now. All right. So what is it that we should actually understand? Number one, what is a matrix? A matrix is an array of elements, you might need to write that, which are usually numbers set up in a pair of brackets. Okay, so that's what we call a matrix. A vector, like I've just said already, a vector is a simple example of a matrix with just one column. So when we write a vector like this, A, B, this is a matrix. It's 2 by 1, one column. Okay. When we are reading a matrix, we describe a matrix using the rows and columns it contains. So we start with rows, then we start by mentioning rows, then we mention the column of that matrix. Okay. So when you look at this matrix here, it's a 2 by 2. But when you look at this matrix here, it's a 2 by 4 because there are 4 columns, the vertical ones. So it's rows, then columns. Okay. And in general, we speak of a matrix as in n by n, where n refers to the number of rows and m refers to the number of columns. Okay. Important definition. A matrix which is called a square matrix, as the name square, if you can recall from it, even if when we're talking of two-dimensional shapes, a square has got all sides that are equal, isn't it? So even in matrices, it is a matrix whose number of rows and columns are the same. So a good example of a square matrix is this example here. This is a square matrix. This 2 by 2 here is a square matrix. So a square matrix must have equal number of rows and columns. Okay, an identity matrix, a zero matrix, is one in which all of the elements are 0. Okay, that's a zero matrix. It's denoted by O. So if I write something like this, even though it's a square matrix, what type of a matrix is this? It's a square matrix, but at the same time, it's also what? A zero matrix. If I write a matrix like this, 0, 0, 0, 0, 0, 0, this is not a square matrix, but it is a zero matrix. As you can see, it is a zero matrix. So that's what we call a zero matrix, okay? An identity matrix is a square matrix. Important definition here. It is a square matrix, number one. But the reason why it's called identity, it is because the leading diagonal. So in a matrix, a leading diagonal is that, I mean, a diagonal is just, it cuts from one vertex to another, isn't it? That's a diagonal. So the leading diagonal in any shape, because we read from left to right, is starting from where? From the left. So if I write I is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, the diagonal that I'm calling leading is this one, starting from the left. I shouldn't have put the 0 there, but that's the leading diagonals. Are we together? And if that leading diagonal is just made of ones, then we call it a what? An identity matrix. So an identity matrix is square, but it has got leading diagonals as 1, and everything else is 0. And we denote an identity matrix with an I. So I can write I2, which means I'm talking about an identity matrix, which is what? A 2 by 2. I can write I4, which means I'm talking about an identity matrix that looks like this. So you have to, the donation is, the symbols we use is very important, okay? I for identity, O for zero matrix. In our presentation, in the questions that you're going to deal with in the exams, the matrix are presented with a bold letter. they will always use a bold letter to show that they are referring to a matrix. That's basically the background to matrices. So one of the objectives after defining what is a matrix, identifying a zero and identity matrix, one of the objectives is to be able to add and subtract matrices, okay? So one of the objectives is to be able to add and subtract matrices. I will use these examples. You should okay. All right, let's move on. Okay, so let's start by identifying the size of this matrix. Like I said, whenever you are identifying the size of a matrix, you start by what? The rows, then the what? The columns. So the size of this matrix is a what? This is 2 rows, so it's 2 by 2. So this is 2 by 2. What about B? Because there is only 1 row, you're going to say it's 1 by 3. C, it's now 2 by 1 because the rows are these horizontal ones. So there are 2 rows, but 1 column. Then this is going to be 3 by 2. That's how we identify the size of a matrix. The matrix rank as well. Okay, to add and subtract matrices, this is very important. You add or you subtract the corresponding elements in each matrix. So when you are adding matrices or you're subtracting matrix, you are looking at the corresponding elements in each matrix. So what does that tell us? What does that tell us actually? If we are looking for corresponding elements, it means you can only add or subtract matrices that are of the same size. You can't add matrices that are not the same size because the method of adding or subtracting is to add or subtract the corresponding sides. What do I mean? Let me just call this 1, 2, -1, and 3. Let's check this one. 3, -1, 0, 2, 1, -3. The reason why, okay, before I do that, I need to, let me do this. So when I'm saying you add the corresponding, you are saying this 2 is going to add the 3, because these 2 are corresponding to each other. So your answer will be 5 here. And this -1 is going to add this 2. So -1 plus 2, 1. This 1 here is going to add this -1, you get 0. And this 3 is going to add this 1, you get 4. So when we are adding or subtracting, we only look at the corresponding matrices. So you can only add matrices that are the same size. Because if I had A, B, C, D plus E, F, G, H, I, J, can I add this? Because the corresponding side is A and E, B and F, so G does not have a corresponding element. So you can't add, so this is not possible. Are we together? You can only add matrices that are the same size, okay? So in simple terms, we say if matrices can be added or subtracted to each other, they are additively comfortable. All right. Quickly. So if I'm to add these matrices, as I said, we're looking at the corresponding sides, is going to be 2 plus minus 1, which is 1. Then it's going to be 2 plus 4. Sorry. 2 plus 4. Are we together? We're here, right? Yeah. So this is minus 1 plus 4, 3. Thank you. 0 plus 5, 5. Then 3 plus. So this is going to be 6. Yeah. I don't know where I was calling my numbers from. Anyway. But the reason why we can add this, they're additive comfortable because they have the same size. If you look at the B, this is a 2 by 3, and this is also a 2 by 3. So yes, we can add them. So it's going to be 1 minus 0, which is 1, minus 3 minus 2, because this minus goes to the 2, which is minus 5, 4 minus 1, which is 3. 2 minus minus 5, minus 3. 1 minus minus 2, minus 1. 1 minus minus 3, minus 2. That's it. That's exactly how you add matrices. Okay? Next point, to multiply a matrix by a scalar, you multiply every element in the matrix by that scalar. What do you mean? I mean, by now you understand what's a scalar. It's just a quantity, isn't it? It doesn't have direction. So a scalar is a number rather than a matrix, any number, okay? So in this topic, all scalars are represented by non-bold letters and numbers. Okay? Yeah. So a good example is this one. A, as I have said, we use a bold letter to denote what? A matrix. Bold letter. So to find 2A, in fact, what 2A means is we are multiplying the matrix A with a what? With a number 2. What do we call this number 2? It's a scalar. So this simply means you're multiplying 2A like this, in bracket 1, minus 1, 2, and 0. So the answer is 2 times 1, 2, 4, minus 2, and 0. Every element in the matrix will be multiplied to that scalar quantity. Okay? Half B means you're going to say half times B, which is a 1 by 3 matrix, which is 6, 0, minus 4, and your answer is 3, 0, minus 2. Okay? If you are to explain why you can't add matrix A and B, I've already mentioned it. You can only add matrices that are of the same size. So why are we not able to add A plus B? Is because A plus B are not the same size. A plus B are not the same size. So you can't add or subtract them. But in this case, we're just adding, so you can't add them. Okay. All right. Then so next example, quickly copy it with me. A is a 2 by 2, B is a 2 by 2, C is a 2 by 2. Perfect. So we want to find A plus 2B, A plus 2B, which is equal to C. However, A, 1, 0, and 2, plus 2B, which is also 1, B, 0, and 3. If we simplify this, maybe I can put another step is A, 1, 0, 2, plus 2, 2B, 0, and 6. This further gives us A plus 2 with corresponding elements. And this gives us 2B, this gives us 1, this gives us 8. So A plus 2B gives us that answer. Are we together? But we want to find the values of A, B, C. So what do? We have got A plus 2B. We have to say it is equal to C. So as a result, A plus 2B, which we know is A plus 2 with a 1 here and a 2B here and an 8 here, is equal to C, and C is 6, 1, 6, C. So the fact that they are equal, it means what? Corresponding elements are the same, isn't it? So it means corresponding elements are the same. So in this case, A plus 2, this element A plus 2 is the same as what? As 6. So the value of A is 4. This 2B here is also corresponding to 6. So the value of B is 3. This 8 here is corresponding to C. So the value 8 is corresponding to C. So that's the value of C. Okay? Solved. All right. So you are able to multiply a matrix with a scalar. You are able to add or subtract matrices. And you understand what is a zero matrix. You understand what is a square matrix. And you understand what is an identity matrix. Okay? All right, quickly. All right. So looking at the two matrices P and Q, first of all, P is a 3 by 3 and Q is also a 3 by 3. So we can say these two matrices are what? What's the correct term? They are additively comfortable. Perfect. So they are additively comfortable. What are we supposed to do? We are told that A, B, C, D, and E, the unknown elements, are just constants. So given that P minus KQ is equal to 0, we understand that a zero matrix is a matrix whereby all the elements are what? In it are zeros. So P minus Q equal to 0 can be presented as 0, A, 0, 2, 0, B. I'm just quoting matrix C, P, and minus 1 like this. Then minus K, then I'll write Q, which is 0, 3, and 0, minus 1, D, and 2, minus 1, 0, and E. And this is equal to 0. So the zero matrix here has to be also a 3 by 3 because this is additively comfortable. So it's going to be 0, 0, 0, 0, 0, 0. So that we've got corresponding elements in here. Of course, this means I but normally in the exam, you would probably skip this part. That's a C here, 0 and minus 1. Excuse my handwriting so small. This is going to be what? You can choose to leave the minus here if you want to. Then you just multiply the K, you get 0 here, you get minus K here, you get minus K there, you get 3K here, you get DK, and then you get 0. You get 0 again here, you get 2K, and then you get EK, and it's still equal to zeros.
You have to like do it all like that, or be like, because the 2 and the minus 1 are in the same spot in like the first row, second column, you find K from that. So like K, 2 plus K equals 0, so K equals minus 2.
Yeah, you can do that, but right now, if you've identified that quickly, you can. But right now, there is a chance that you might have some equations as well to solve other variables. As you can see, like perhaps if we look at it, this 2 minus 2K, yes, you can find the value of K. But what about B? B and 2K is equivalent to that. Okay, yeah, so you can still eliminate this and do that. But this is the perfect way to get to a system of 5 unknown questions. Is it 5? Actually 6 unknown variables. But it's all right. So we are going to have here 2 plus K, isn't it? Because remember, this is 0, and this is 2 plus K, and this is C plus K again, and this is A minus 3K, and this is 0. Okay, I don't need to write the 0, but this is just minus DK. And then that's 0 again. This is a 0 again. This is B minus 2K. And this is minus 1 minus EK. And it's all equal to, let me not write this, I can just write 0 here. It's okay, isn't it? To just write a 0 like this, then we know. So like Taylor has said, we can now say 2K plus K, 2K plus K, 2 plus K is equal to 0. So K is minus 2, right? And we know again, C plus K is 0. So C is equal to minus K, which is just equal to minus 2. So C is 2. Following? What else do we need? A minus 3K, A minus 3K is equal to 0. So A minus 3 and K is minus 2 is equal to 0. So A is minus 6. All right. B minus 2K. B minus 2K is equal to 0. B minus 2, but K is minus 2 is equal to 0. So B is equal to minus 4. I'm sure we found everything. No. 1, 2, 3, 4. DK, yeah. Minus DK is equal to 0. So however it is, D will always be 0. It doesn't change anything. Then we can find E. There is our E. So it's important. Now, that's what I was trying to say. You might lose some question marks here because it's minus 1 minus EK, which is equal to 0. So if you just try not to write this, you might not see it clearly. All right, so this is going to be minus 1. So it's going to be minus E, and K is minus 2 is equal to 1. And this is going to be 2E is equal to 1. So E is actually equal to half. We're done. All right. You can actually finish that on your own. All right. Next part. Matrix multiplication. It's also very important to get definitions of important points of multiplication. Matrices can be multiplied together if the number of columns in the first matrix is equal to the number of rows in the second matrix. Okay? The number of rows of columns in the first is equal to what? In the second. So what does that actually mean? If A, let's say A is an M by N, in order for me to multiply A to B, how many columns do we have in A? How many columns do we have in A? Columns. Columns. N. So there are N columns in A. So in order for us to multiply A to B, B must also have what? N rows. N rows. So it can be, so in order for this to be multiplied together, it's going to be M times N, then B has to be N times whatever you want to call it here. The condition is that these two, I can call it S here, these two must be the same. The first rows of the first matrix must be the same, first columns of the first matrix must be the same as the rows of the second matrix. And what will be our answer in this case? Our answer will be C, which is going to be an M times S matrix. Do you understand that? Do you understand that? Okay? So the number of columns of the first matrix must be the same as the number of columns, rows of the second matrix. Now, this is crucial. How is it so crucial? It actually tells us that AB is not going to be equal to what? BA. Because normally in numbers, the commutative law is applied, isn't it? A times B is the same as B times A. But in matrices, it can't be. Because if you look at this example here, AB, you see that BA, B is N times S, and A is what? M times N. Now, do you see what's the problem? These two are not the same. So we can multiply BA times A. Because whenever we are multiplying matrices, the first column of the first matrix must be the same with the first rows of the second matrix. You see, so it's not always going to be in a matrix that A times B is equal to B times A. There can be situations, like if you're dealing with square matrices, okay? It's possible, but it's not always the same with any other matrices. Because that's the rule of multiplication, okay? Understood? And when you multiply a matrices, the size that you get is going to be the number of rows of the first matrix times the number of columns of the second matrix. That's the answer that you get there. Okay. All right.
Well, which numbers?
What do you mean?
9. How did they get 15 there?
Okay, we'll get there.
Oh, okay.
All right. So A is not always equal to AB is not equal to BA, except if they are both square matrices. Okay. If AB exists, does not mean that BA exists. Okay. Does not mean that. I've just given you an example. So you can also use that. Because if you look at A, if A is 3 by 2 times B, which is 2 by 4. Yes, this is okay. Because these two are the same. So we are going to get a C, which is a 3 by 4. Are we together? Do you see that? But if we have got A, if we've got B, which is a 2 by 4, times an A, which is a 3 by 2, this is not possible. Because this is the same, not the same. So it's always never going to be like that. Are we together? Except when we are dealing with square matrices. All right. Important point. I'm sure you've copied it already while I was explaining. Now, to find the product of two matrices, if they are multiplicatively comfortable, that is the number of the columns of the first matrix is the same as the number of rows of the second matrices. You multiply the elements in each row in the left-hand matrix by the corresponding elements in each column in the right-hand matrix and add the results. That's quite a very long statement, but you understand it anyway. It's self-explanatory, but I'm going to show you now what we mean. Okay? Make sure you pay attention on that. All right, so we multiply the elements in each row in the left-hand matrix by the corresponding elements in each column. So what does that mean? The left-hand matrix is this one. So the first row is this one. Are we together? So we're going to multiply this row with this column because it's row times column, and we add. We multiply the corresponding elements and we add them. So what are we doing exactly? What does that mean? You are going to say 5 times, let me write it here. You're going to say 5 times 2 plus minus 1 times 9 plus 2 times 7. Are we together? So you multiply the corresponding elements of the row versus the column, then you add them together. When you add them together, you get 15. This is where this 15 is coming from. Are we together? For the next number 21, you take the same row, you multiply it with what? Second column. So you're going to say 5 times 2 plus minus 1 times minus 3, this minus 3, plus 2 times 4. When you simplify this, definitely get 21.
Period 3 has ended.
Okay? Then you are done with the 2 elements of the first row. You go to the down, you do